Hello students, welcome to aimsindia online classes. This is a chemistry session. Here we are discussing about the classification of elements. In the earlier sessions we have seen about the earlier classifications, in which manner scientists they have tried to classify the elements, and Mendeleev's periodic table also have seen, isn't it? So now in this session we are going to say about modern periodic table, which we observe in our classrooms or in our schools nowadays. That is called modern periodic table, but it was not the first one. Earlier to that, so many scientists they have tried to classify the elements, those we have seen. Now let us see about this modern periodic table, how it is designed, on which basis it is constructed, those we are going to see now. HJ mostly found that each element emits a characteristic pattern of X-rays when subjected to bombardment by high-energy electrons. So by analyzing the X-ray patterns, Moseley was able to calculate the number of positive charges in the atoms of respective elements. So the number of positive charges or protons in the atom of an element is called atomic number of that element. With this analysis, Moseley realized that the atomic number is more fundamental characteristic of an element than its atomic weight. So we have learned that Mendeleev's periodic table is constructed based upon the atomic weights of the elements, and thereby there were some limitations because of the selection of atomic weight as basis. But mostly for the first time he identified atomic number is a most or more fundamental characteristic than atomic weight for an element, because in X-ray diffraction experiments each element is emitting characteristic pattern with X-rays. So it is being different from one element to another element in these X-ray patterns. So from this analysis, he concluded that atomic number is more fundamental characteristic than atomic weight of an element. After knowing the atomic numbers of elements, it was recognized that a better way of arranging elements in the periodic table is according to the increasing order of their atomic numbers instead of atomic weights. So till Mendeleev, all the scientists they have considered atomic weight as a fundamental unit or fundamental basis for classification of elements. But for the first time, mostly he concluded and he analyzed and he has given conclusion that atomic number is more appropriate, and it is a fundamental unit which can be chosen for classification of elements. Okay, so this arrangement eliminated the problems of anomalous series. So based upon this atomic number basis, he categorized the elements, and then there it eliminated the problems arised due to this atomic weight series. Some problems like anomalous series and even isotopes, placement of isotopes in the periodic table. These all problems which were faced by this Mendeleev periodic table were eliminated. How? By choosing atomic number as the basis instead of atomic weight. For example, though tellurium has more atomic weight than iodine, it has atomic number less by 1 unit compared to iodine. So this atomic number concept forced the periodic law to be changed. Actually, what happened in the Mendeleev's periodic table, he kept tellurium, which is having greater atomic mass or atomic weight, before the iodine, which is having lower atomic weight. So there Mendeleev's periodic law was not followed, we said already, isn't it? That's why it is called anomalous pair, the pair of elements where Mendeleev could not follow his periodic law, that is increasing order of atomic weights, because he wrote here tellurium with greater atomic weight first, then the iodine with the lower atomic weight. But if you take the atomic number into consideration, iodine is having, tellurium is having lower atomic number than that of iodine. So there is no problem now. So in this way, the periodic law is changed. Instead of being atomic weight, now atomic number came into alignment. So it is taken as consideration. The periodic law is changed from atomic weight concept to atomic number concept, and now it is called modern periodic law or Moseley's periodic law. We know that Mendeleev's periodic law is stated as the physical and chemical properties of the elements are the periodic functions of their atomic weights. So what does it mean, the law? When elements are written in the increasing order of their atomic weights, the physical and chemical properties of the elements are periodically repeated from one element to another element. That is the periodic law which was given by Mendeleev. So in the honor of his name we call this as Mendeleev's periodic law. Statemental it is given as the properties of the elements are periodic functions of their atomic weights. Isn't it? Now let us try to understand modern periodic law. The modern periodic law may be stated as the properties of the elements are periodic functions of their atomic numbers. That means when elements are written in the increasing order of their atomic numbers, the physical and chemical properties of these elements periodically repeated from one element to another element. So then the elements which are getting the similar properties will be written one down to another. In that way, this modern periodic table is constructed based upon the atomic number, right? Based on the modern periodic law, the modern periodic table is proposed or constructed. It is an extension of original Mendeleev's periodic table, known as a short form of table. And this modern periodic table is called the long form of the periodic table. Because if you say Mendeleev's periodic table contains only 8 columns, of course with the two subgroups each again. But when the atomic number is taken as a basis for classification, then totally in the modern periodic table, which is constructed based upon the modern periodic law, it contains totally 32 columns or 18 columns we say generally. That's why it is called long form of the periodic table, and Mendeleev's periodic table is called short form of periodic table. Okay? Yes, this is modern periodic table, which is constructed based upon the modern periodic law and atomic number as the basis. All the elements are written in the increasing order of their atomic numbers, and those elements for which properties are being periodically repeated from one element to other element, they are written one down to another. For example, if you say hydrogen is written first, and next increasing order number helium is written here. Now, next element lithium is having chemical and physical property resemblance with hydrogen. So it is written down to hydrogen. And the elements are written in the increasing order again, continued here. And again, after a certain time, sodium is one more element which is getting similar chemical properties as lithium and hydrogen. So it is written down to those again. And they are continued here. In this way, this periodic table is written based upon the atomic number and modern periodic law. See how many columns are there totally here? 18 vertical columns are there. So that's why it is called long form of periodic table. Actually to say not only 18 columns, totally there are 32 columns in this modern periodic table. If you observe, there are two separate horizontal rows with 14 elements each. These elements to be kept in this place. So these elements to be kept in this place. So first two columns and again these 14 columns and near remaining 16 columns. Total becomes 32 columns in the modern periodic table. That is why it is called long form of periodic table. So to avoid the inconvenience in writing, these 14 elements are written separately here at the bottom of the table. Now it became with 18 columns, which we call as groups. Okay, in the same way here, these elements to be placed in this position, 14 elements. Okay, this is about a long form periodic table. Atomic number of an element indicates not only the positive charges, that is protons, in the nucleus of that atom, but also the number of electrons in the neutral atom of that element, isn't it? Atomic number represents number of protons in the nucleus. At the same time, number of electrons also which are revolving around the nucleus. But in the neutral atom, number of protons and number of electrons will be same, which both represent atomic number of that element. The physical and chemical properties of atoms of the elements depend not on the number of protons, but on the number of electrons and their arrangement in the atoms. Yes, the chemical properties of an element depends upon the electrons revolving around the nucleus, but not on the number of protons present in the nucleus. So the characteristics of an element depends upon the electrons which are revolving around the nucleus for an atom. That we say that representation of the electrons around the nucleus we call as electronic configuration. Now we can say simply the properties of an element depends upon its electronic configuration, isn't it? Yes. Therefore, the modern periodic law may be stated as the physical and chemical properties of an element are periodic functions of their electronic configurations of their atoms. Yes, instead of atomic number, we can say electronic configuration also. So this atomic number and electronic configuration both are taken into consideration while constructing this modern periodic table, because the properties of the elements are depending upon the electronic configuration of the atom. So the electronic configuration is based upon the number of electrons. Number of electrons is depend upon the atomic number. So we can say the periodic law, the modern periodic law in terms of electronic configuration as well as in terms of atomic number, both we can say. So these two are taken into consideration while constructing this modern periodic table. Elements are written in the increasing order of their atomic numbers, and the elements which are getting similar valence electronic configuration, similar kind of outer shell configuration are written one down to other, and those all elements are having similar chemical properties, right? Next, positions of elements in the modern periodic table. How these elements are positionized in the periodic table. The modern periodic table has 18 vertical columns known as groups and 7 horizontal rows known as periods. Yes, totally there are 18 vertical columns which are called as groups, and these 18 vertical columns broadly classified into 8 main groups, and again each group divided into 2 subgroups A and B. So we can say 16 groups or 18 columns or 8 groups. Nothing wrong. All are correct. Okay. Let us see what decides the position of an element in modern periodic table. We can explain the classification of elements in the modern periodic table in terms of certain electron arrangements which are periodically repeated. The elements with the similar outer shell configuration, that means valence electronic configuration, in their atoms are in the same column called groups. Yes, we told here how this modern periodic table is constructed based upon atomic number and electronic configuration, mainly valence electronic configuration. How it is done? Elements first, they are written in the increasing order of their atomic numbers, and their electron configuration is also taken into consideration. The elements with a similar valence electronic configuration are written one down to another, which we call as a group. So those all elements will be having in a column will be having same valence electronic configuration, and hence they exhibit the same kind of properties. Okay. Elements listed in a group down to 8 are in the order of their increasing principal quantum number. Principal quantum number represents shell number. So the elements which are present in a group, if you observe from top to bottom, the shell number will be increased gradually one to another. For example, if you see hydrogen, what is the valence electronic configuration of hydrogen? 1s1. So the last shell is 1. If we see next element to hydrogen, that is lithium. If we see configuration of lithium, 1s2, 2s1. So what is the last shell number? 2. So from hydrogen to lithium, it increased by 1. And next if you see for sodium, 3s1, it is increased by 1 unit. Okay, in this way, principal quantum number gradually increases as you move from top to bottom in a group. In the chapter Structure of Atom, we have learned that S subshell with one orbital contains a maximum of 2 electrons. Isn't it? Yes, S subshell contains only one orbital which can accommodate only 2 electrons. If you see p subshell, each p subshell contains 3 orbitals and each orbital can accommodate 2 electrons and hence maximum of 6 electrons. So p subshell can accommodate 6 electrons. And if you see the D subshell has 5 orbitals. We know each orbital maximum can accommodate 2 electrons. Now how many electrons it can accommodate D subshell? Total of 10 electrons maximum. And if you see F subshell contains 7 orbitals. 7 into 2, 14 electrons maximum can be accommodated into F subshell. So this is our accommodation capacity of subshells. S subshell can accommodate only 2 electrons. P subshell can accommodate 6 electrons. D subshell can accommodate 8 electrons. And F subshell can accommodate total 14 electrons. Okay. Depending upon to which subshell the differentiating electron enters in the atom of the given element, the elements are classified as S, P, D and F block elements. Yes, based upon the position of the differentiating electron. What is meant by differentiating electron here? Differentiating electron means the last electron of that element or the last coming electron. So to which subshell that last coming electron enters in an atom, the position for that element is given based upon that in different blocks. So total, the modern periodic table is classified into 4 blocks based upon the subshell into which the differentiating electron entering for the elements. Okay. For example, sodium gets its new coming electron or differentiating electron into 3s level, isn't it? Yes, because sodium has 11 electrons, and if you see its configuration, electronic configuration, 1s2, 2s2, 2p6, 3s1, means it is having its outermost electron in its 3s subshell. Okay, because 11 electrons, if you see its configuration, 1s2, 2s2, 2p6, or the last electron configuration, 3s1. So for sodium, the last electron which we are calling here as differentiating electron, it is present in its s subshell. Therefore sodium is an s block element. Okay, now if you see aluminum, aluminum gets its differentiating electron into p subshell, because if you see electronic configuration or atomic number of aluminum, 13, and if you see configuration, 1s2, 2s2, 2p6, 3s2, 3p1, isn't it? Yes, because its atomic number is 13. So 13th electron or the last electron, which we are calling here as differentiating electron, it entered into p subshell of aluminum. So we can say now aluminum is a p block element. Similarly, if you see for scandium, its atomic number is 21. If you write the configuration, we can identify there its last electron, 21st electron, entered into d subshell. So we can say scandium is a d block element. In the same way, for cerium, last electron or differentiating electron enters into f subshell. So it is hence it is called f block element. Okay, based upon the differentiating electron entering into a particular subshell, all the elements in the periodic table are categorized into 4 blocks. They are S, P, D and F blocks. So let us observe the electronic configurations of the elements which you have seen now. The last coming electron is underlined here. Observe carefully the configurations so that we can understand how these blocks are categorized in the table. First, if we see sodium, what did you say its atomic number? 11. If we see its configuration, what do we get? At last, 3s1. Differentiating electron for sodium is in S subshell. So it is a S block element, isn't it? If we see next, one more element, aluminium. Its atomic number is 13. If its configuration is written, it is having last electron in its p subshell. So it is a p block element. Next, we have written there scandium, whose atomic number is 21. If we write configuration for 21, we get it as 1s2 2s2 2p6, 3s2 3p6, 4s2 3d1. So its differentiating electron is present in d subshell, hence it is a d block element. Now let us see for the fourth one, cerium, whose atomic number is 58. If the electronic configuration is written for this 58th element, its last electron or differentiating electron is present in F orbital or F subshell. So it is a F block element. See here, the differentiating electron is present in F subshell. So it is a block element. Got it? So this is a overall classification of elements into four blocks. See, if it is considered as a modern periodic table, the last two columns or the extreme left side two columns will be containing their differentiating electron in their S subshell. So they are called S block elements. And here these elements, extreme right side six columns elements except helium. For these all, differentiating electron is present in P block or P subshell. So they are called P block elements. In the same way, the middle 10 columns, we say this is a third B group, third B to second B. Means third B, fourth B, fifth B, sixth B, seventh B, and these three columns are called eighth B, and here 1B to 2B. These 10 columns elements, they are containing their differentiating electron in D subshell. So they are classified as D block elements. And we discussed at the starting, certain four elements are written at the bottom of the periodic table to make it convenient. 14 elements. Cerium to lutetium, thorium to lawrencium. These elements are having their outermost electron or valence electron in their F subshell. So they are considered as F block elements. Okay, let us see in detail about these blocks once again. S block elements. So these are the first two columns in the modern periodic table. These are called S block elements because for these elements their differentiating electron entered into S subshell. Okay. Next, if you say P block elements, these are the last six column elements. Of course, here out of these six columns elements, only helium is accepted from this P block because even though it is extreme right side along with the remaining noble gases, it does not contain P electrons, isn't it? Because if you observe its configuration 1s2, it is having its differentiating electron in S subshell. So it should be at the left side actually. But because of its chemical inertness and similarity in properties with these elements, it is kept in the P block, even though it is S block element. That's the only exception for the remaining all elements from third A to eighth A group. For these all elements, differentiating electron in the P subshell, so they are P block elements. So these groups are third A to eighth A. Okay. If you see next D block, the elements in which the differentiating electron enters D subshell are called D block elements as we told. So these 10 columns. What we can say here? Third B group. Third B to second B. This is first B. These three are eighth B. In this way, these 10 columns elements are called D block elements for because for these elements differentiating electron is present in their D block or D subshell. That is to say clearly penultimate energy level D subshell. Penultimate means last but one shell. Next, F block elements. For this, the differentiating electron is present in F subshell of anti-penultimate shell. Anti-penultimate means the shell last but two. Okay. So the two horizontal rows which are written separately at the bottom of the periodic table are considered as F block elements. Okay. These are the placed at the bottom of the periodic table. So let us recollect once the new terms which we have used here. The outermost shell we call. Outermost shell means the last shell of an element is called its outermost shell. One more term we have used that is a penultimate shell. Penultimate means last but one shell. Suppose it is an atom. Its outermost shell is called valence shell. And the last but one shell. This is called penultimate shell. And the last but two from the outside, the third shell is called pre-penultimate or anti-penultimate shell. Okay, that is about the classification of elements into the modern periodic table and classification into four blocks. Right. Thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates and recorded videos.